Hello and welcome back once again to this lecture series on aluminum based alloys and metal matrix composites.
Okay, so right now we are discussing about this precipitation hardening. We have discussed the mechanisms of hardening in the past couple of classes. And we have seen that there are basically 6 different mechanisms through which the hardening can occur in this particular phenomenon. And then we also talked about the precipitation sequence. For a particular age-hardenable alloy, there is a particular sequence in which the precipitation occurs, and we actually discussed about one of them, taking the example of one of the alloys, that is aluminium copper, and we have seen that it goes through a sequence which includes 3 intermediate phases before the equilibrium phase theta forms, right? So we have seen that it starts from the supersaturated solid solution and then goes through these phases GP1, GP2, then the theta prime precipitate forms, and ultimately the equilibrium phase theta forms, right? So depending on a particular alloy system, there is a particular sequence in which the precipitation occurs. And that is what we are going to talk about, taking all the age-hardenable aluminum alloys that we have. And for each of them, we are going to discuss about this particular sequence. So let us again start with the 2000 series. This is basically the aluminum copper system. And in fact, this was the system through which the age hardening phenomenon was actually discovered. As I talked about this, in one of the classes as to how this whole phenomenon of age hardening was discovered in case of aluminum alloys. And the alloy which was being investigated was actually an aluminum copper alloy. And that is why you would see all the examples of precipitation hardening mostly talks about this particular alloy in case of aluminum alloys, right? In most of the textbooks, you would find that the precipitation hardening has been described by taking the example of aluminum copper alloys, because once that age hardening was discovered in this particular alloy, it was subjected to extensive investigation with regard to this particular phenomena with respect to age hardening, and that is why you get the example of this alloy system with regard to precipitation hardening everywhere. Okay, so let us start with that first. And in fact, we have already talked about this, so a little more into that. Let me give you a little more detail as to what exactly are those phases which form during the precipitation hardening of this particular alloy. So this is the sequence that we have already seen. GP zones are nothing but the cluster of copper atoms, as we have discussed before. And this form on a particular plane, in this case it is 100 planes. And if you talk about the size of these GP1 zones, the thickness is about few interatomic distance. And these clusters are surrounded by aluminum atoms and vacancies. So as the aging progresses, as the aging continues, the size of the GP zones will increase, and then it will reach a constant size after a while. The size depends on the aging temperature. For example, at room temperature, it's about 3 to 7 nanometer in size. While if you talk about an elevated temperature such as 100 degrees Celsius, the size will grow to about 10 to 15 nanometer. Okay. And the size does not really depend on the copper content, but the copper content will actually affect the number of GP zones rather than the size. For example, if you talk about 4% copper, the number of GP zones is in the range of 10 to the power 14 to 10 to the power 15 per millimeter cube. And the spacing between them is of the order of 2 to 4 nanometer. And this is at room temperature. The next phase which forms in this alloy is the GP2 or the theta double prime. These are disc set and are larger than GP1s. Talking about the size of GP2, the diameter is about 30 nanometer and the thickness is about 10 atomic planar distance. That's typically about 4 nanometer. That's the thickness. Okay. But their number is lesser compared to GP1. And this is tetragonal in terms of the crystal structure with lattice parameter A close to that of aluminium, that is 4.05 angstrom, and C is equal to 0.77 nanometer. And the structure basically consists of alternate layers of copper and aluminium atoms on the 100 planes. The next in the sequence is the theta prime precipitate, which has a similar chemistry as the equilibrium phase, but this is an intermediate phase before the equilibrium phase forms. And if you see their characteristics, these are plate shaped, and the size depends on the aging temperature. And also the aging time. Typically, they can be having a diameter in the range of 10 to 600 nanometer. And thickness in the range of 10 to 15 nanometer. And these precipitates are semi-coherent with the matrix. And therefore results in coherency strain, as we have discussed before. And finally, as you continue the aging, the equilibrium phase theta forms. This has a tetragonal crystal structure. And as we have discussed, this is no more coherent with the matrix and also coarse in size. And therefore, when this phase forms, the hardness decreases. We'll also talk about some of the alloys in each of these alloy systems. So when you talk about the 2000 series, a very popular alloy is this one, 2024. This has a composition of 4.4% copper, 1.5% magnesium, and some amount of manganese. So when you have a second alloying element present, which is magnesium in this case, the precipitation sequence and the precipitate can also change. Okay. So for example, in this case, when you have magnesium as the second alloying element, you can have the GP zones forming, but the composition of the GP zones will change because now, apart from the copper atoms, the magnesium atoms will also join the GP zones. So this will be basically the cluster of both the atoms, copper as well as magnesium. And the precipitation sequence will be like this. And now the precipitate will also be different because we have magnesium joining in along with copper. So instead of CuAl2 or Al2Cu, it will be Al2Cu-Mg because now Mg has also joined, right? And after that, the equilibrium phase will be S, which is similar in composition to the S prime. So this is going to be the precipitation sequence, and the precipitate will be S prime when you have magnesium present along with copper. And there is a high purity variety of this particular alloy, which is 2124. Here the high purity is maintained by keeping iron and silicon to minimum level. Rest of the composition will remain the same, and these two are kept at minimum to ensure a high fracture toughness. And this particular alloy, this 2024, is used in T8 condition. Which is solution treatment followed by cold working and then artificial aging. And this cold working is given to ensure that you have enough number of nucleation sites for the S prime precipitate to form. Okay, so when you have this deformation given to the material, as you know, more dislocations will be generated, and these dislocations will now act as heterogeneous nucleation sites. Along with that, the grain boundaries will also act as the heterogeneous sites for nucleation. Right, so this is why the cold working is given, so that more number of S prime precipitates can form. If it is simply solution treated and aged, the number of dislocations are not that great. The dislocation density is not really high, and therefore the S prime precipitate may not form as uniformly or in the number which will give rise to a high hardness, right? So therefore, in order to ensure that it forms uniformly in large number, this is given a cold working before the artificial aging, so that the defects like dislocations and grain boundaries can act as the nucleation sites for the heterogeneous nucleation of the S prime precipitate. And if you look at the properties in this condition, the yield strength, which is for aluminum alloy basically the 0.2% proof stress, is 415 MPa. And this kind of alloys in T8 condition are used for parts of aircrafts. It can also be used in T3 and T4 condition. T3 condition is nothing but solution treated plus cold working followed by natural aging, and the yield strength in this case is around 350 MPa. And in T4 condition, which is natural aging, it gives around 290 MPa proof stress. Next we have the 6000 series. This is aluminum, magnesium, silicon alloys. And here the sequence is as follows. Here the main precipitate is beta prime or Mg to Si, and the equilibrium phase is beta having similar composition, that is Mg to Si. Okay. Here the GP zones are spherical. In the beginning, but get elongated as the aging is continued. And they get elongated in the 100 direction. And as a result, become needle shaped. These GP zones basically consist of magnesium and silicon atoms. And here the mismatch with the lattice is not that great. Mismatch with the matrix lattice. So beta prime is the intermediate phase which forms before the equilibrium phase beta forms. And these are semi-coherent with the matrix. And are rod shaped. With length about 1 micron. And diameter of about 0.1 micron. Okay, so this is the precipitation sequence for the 6000 series alloys, where the main precipitate is the beta prime. And as I said, beta of course is the equilibrium phase. And this has a FCC lattice with the lattice parameter 0.639 nanometer. And in terms of the morphology, the beta phase is plate shaped. Okay, so this is about the 6000 series alloys.
And with that, we come to the end of this lecture. Thank you for your attention.